Hello everybody, it's Mr. Keeney, and we are here with Section 2.2 Day 2 notes. So it's actually our third section notes of Unit 2 Part 1, and we are going to continue talking about deductive reasoning to form logical arguments, and again we're going to be talking about conditional statements. So Day 2 of it, we're going to see some different things. We're going to see this applied directly to geometric terms that you've probably heard in the past. So let's go ahead and jump into it here. We're going to start off with an example. It says, if an angle is a right angle, then its measure is greater than that of an acute angle. And we got four little questions. It says, A, is the conditional true or false? So let's think about this here. If an angle is a right angle, its measure is greater than an acute. And an acute angle is anywhere from 0 to 89 degrees. And actually, let me adjust that. Actually, not even 0. It's anywhere from 1 degree to 89 degrees, or I should say bigger than 0. Let me go one more time here. Bear with Mr. Keeney, okay? It is anywhere between 0 and 90. It cannot equal 90, it cannot equal 0, but somewhere between there. And a right angle is exactly 90. So looking at this, is the conditional true or false? We're going to say true. A right angle is exactly 90, which has to be bigger than anything that an acute angle is going to be. The next one says write the converse. Now converse means we're going to switch the hypothesis and conclusion. So if, and instead of saying if it's a right angle, we're going to say if the measure of an angle is greater than an acute angle. If the measure of an angle, this is going to take a while, of an angle is greater than acute, then, and now we're ready for the original hypothesis, which is then it is a right angle. Now this one, we'll think about it. We now know what an acute angle is, anywhere from 0 to 90. And it's saying if we have a measure of an angle that's greater than acute, so bigger, it's 90 or bigger, does it have to be a right angle? This one's false. False, because it could be an obtuse angle. Obtuse is bigger than acute, but it is not a right angle. So is this a valid definition? No, because of this right here, this false meaning. So it kind of fails there. So just a little example, talking about converse and conditional, kind of a review from our last notes. Moving on to something that maybe you've seen in the past with your experiences either in middle school math or an earlier math class in high school, perpendicular lines. And let's just get right to the definition. It says, if two lines intersect to form a right angle, then they are perpendicular lines. You can see down here in the example, L and M are intersecting to form this right angle. That little box tells us that. It says the definition can also be written using the converse. If any two lines are perpendicular, so notice they've switched their conclusion to the hypothesis, which is exactly what the converse here does. It switches hypothesis to conclusion. They intersect to form a right angle. So definitions, and kind of we saw it up here, definitions, they work for the conditional, they work for the converse. So we can write this also geometrically as line L is perpendicular to line M, as L is perpendicular to line M. So perpendicular, that symbol right there, that upside down T, we will use that to say perpendicular, because perpendicular is a very long word, and just like we have symbols for addition, subtraction, multiplication, equal sign, a lot of symbols, we have the upside down T for perpendicular. Okay, so when we have this, when both the conditional and the converse is true, we can write one statement and have, instead of me saying, okay, write the conditional and then write the converse, we can write one statement called the biconditional. The biconditional, and we'll say biconditional statement. And we connect the hypothesis. We connect the hypothesis and the conclusion with this phrase, if and only if. That will be what connects, and we'll put that here in the middle and you'll see some people write it as IFF, which means if and only if. So we're going to say hypothesis, if and only if, the conclusion. Here's an example. So the perpendicular one up here, it says if two lines intersect to form a right angle. So I'm going to write that out, but drop the if. So two lines intersect to form a right angle. And this is where we're going to connect the hypothesis now with if and only if. I'm going to underline it too. That's our connecting. So two lines intersect to form a right angle if and only if. And then the next part is they are perpendicular lines. So a nice way to write the biconditional, which means the conditional and the converse are true. And we can do this with other statements as well. This is actually our last one, short notes today. Example 2, write the statement as a biconditional. So we have if a student is a boy, he will be in group A. If a student is in group A, it must be a boy. So we can see here that we've got two things. So a student is a boy is our hypothesis. If, and I'm going to say if and only if like that. So if and only if they are in group A. All right, and that's actually it for these notes, day 2 of the conditional statements lessons. So there is some material online for you guys to look through and try out for yourselves. With that being said, I will talk to you guys next time. See ya.